They are found nearly everywhere. Elegant, efficient, ever-changing, and nevertheless constant. They are the scientific instrument found in the pockets, backpacks, briefcases, and purses of people across the globe, able to measure things with truly phenomenal accuracy, and yet they cost only a few dollars to make. In the Western world, perhaps nothing has come to more comprehensively symbolize civilization's mastery over the complexity of nature through simple and regular measurement. The scientific, industrial, and informational regularization of our perception of the natural world is characterized entirely by a simple circle, 12 numbers, and 2 hands. They're posted in classrooms and doctors' offices. Businesses still use them, even as other ways to represent the daily passage of time have become available. Yet, as the newest generation of computerized timekeepers, miniaturized to a degree unimaginable just 400 years ago, have more options than can be imagined to show the time of day, one of the most commonly selected options is still the simple representation that holds within its design the idea of a repeated cycle. The simple clock face is a design with roots in antiquity that came to represent in the time of the Industrial Revolution a regularization of a phenomenon that for most of humanity's experience has not been and is often still not regular. As Einstein once noted, the relative perception of time is something intuitive to the human experience. An hour, he said, spent in the presence of another desired can seem like a minute, while a minute on the other side of the bathroom door in a time of emergency can feel like an eternity. This has, for most of human history, been the dominant paradigm of the reckoning of time, and in many places in the world, it still is. Yet with the simple and breathtakingly elegant clock face, the passage of time is now normalized and regularized, divided into intervals, and then counted and cataloged. One of the characteristics of the modern, Western industrialized society is that we have so rationalized time that an illustration like Einstein's is required to remind us that there's another way to think about it. So how did we get here? How did the regular sweep of 2 hands around a circle of 12 numbers come to symbolize the counting of the hours, minutes, and seconds? Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 10.2, Supplemental. A Brief History of Telling Time. The Clock. Well, I managed to survive finals, and so did my students. After a week of logistics and moving, I'm back home from my sabbatical year and gearing up for summer classes. Before I jump into this week's material, let me take a moment to thank Gordon State College for giving me the opportunity to spend the year working in a new and unique environment so that I could learn and bring back new ideas. I also want to thank Berry College for giving me the chance to be a part of their wonderful community for the last 10 months. I would especially like to thank Todd Timberlake, Charles Lane, and Sean Hilbert for a number of conversations and collaborations that will vastly improve my teaching here at Gordon. And if I may take just a moment to veer off on a digression, this project that I have been supported in doing is one of the truly great things about academia. What I've just finished is what's called a sabbatical. While the details of this vary from place to place and institution to institution, the basic idea is that a member of a faculty at an institution takes a period of leave, often paid, from that institution and go somewhere else to collaborate with others doing similar work. In my case, thinking about the best ways to teach physics. In doing this, the person takes his or her work and ideas to share with their colleagues at the receiving institution. In turn, they're also exposed to the ideas and practices of those doing work at the other place. This sort of collegial exchange is vital to the transmission and development of new ideas in the process of both scientific inquiry and the teaching of science. And without it, the spread and development of ideas and innovations would be slowed substantially. So it is with great appreciation that I'd like to acknowledge both institutions and their work to allow me this opportunity. I'd also like to thank the students of Berry College for the privilege of being a small part of their learning and achievement. I wish you all the best going forward. Okay, so where were we? Right, time. Alright, in our last episode, we looked at timekeeping from the perspective of keeping track of the accumulation of days. We examined the development of the modern Western calendar that is used by most of the world today, at least in the planning and scheduling of civil affairs. Of course, this isn't the only form of complex calendar that humanity has developed. The Mayan calendar, another system that was cut loose from the restriction of having to line up with lunar phase cycle, is a technological innovation of startling complexity and subtlety. For those who may have missed our episode on Mesoamerican astronomy, we cover the basic workings of that system there, among other things. This week, we want to take a look at going in the other direction, the dividing of the day into smaller and smaller partitions. This is a story every bit as interesting and compelling as the development of the calendar. Before we go into that, however, I want to be explicit about something that I think I've only implied thus far. Timekeeping is an astronomical function. The way we keep time is tied intimately with the motions of the objects in the heavens. No matter where you go in human history, the practice of keeping time is related to what's going on in the sky. When developing calendars, it usually has to do with the moon at first, and then, as observations improve, the sun. But there can be other celestial objects and their movement that are used to create calendars as well. As we've discussed, the calendar of the Maya seemed to have been tied to the motions of Venus. When we want to talk about dividing up the day, we are really looking at the motion of the sun when it is above the horizon and the stars when it is not. And before we get into the specifics of how we begin to mark the passage of the day in smaller and smaller intervals, I want to have you engage your imaginations with me and return to a time when there were no devices to divide up the day and the night. For most pre-industrial cultures, the beginning of the new day was marked by an event in the sky. The idea of midnight that we use now is a relatively modern invention, probably within the last 3,000 or so years, due to the need to have a cosmology that does not have the sun being swallowed by a supernatural being or traveling to some sort of underworld. That means that for most of human existence, the start of the day was always associated with some kind of solar event. For some cultures, it was the rising of the sun, perhaps marked by that moment when the sun was first visible over the eastern horizon, or when the last star faded from view as dawn spread across the sky. For other cultures, it was the setting of the sun in the west, or the emergence of a star or two in the evening dusk. Between those two times, the day was divided loosely. There was dawn, and then morning. This would have been followed by midday, when the sun was highest in the sky. After this came the hottest part of the day. As the sun approached the western horizon, there would have been evening, and then, finally, dusk, terms we still use now. None of these would have been very well defined, but everybody knew the times. Women gathered at the well to draw water in the cool of the morning. Clothes were washed in the river at midday so that the heat of the afternoon would dry the fabric. People weren't so busy that they couldn't wait and linger for a time, and thus, more precise timekeeping wasn't all that necessary. The night, too, was divided, though not as finely. At dusk, the last chores were tended to, and the hearth fires were brought to life for cooking and light. Quieter tasks were seen to, the repairing and mending of clothes and tools. When the last meal was over and the final tasks complete, the time was given over to sleep, that eternal metaphor for death. And so, for many cultures, the deepest and greatest part of the night was simply known as the dead of night. For those tasked with keeping watch, the passing of time was marked by the movement of the stars through the heavens. For those cultures in the northern hemisphere, no tool was better suited for this than the Big Dipper, however it may have been known by the cultures that named it. Facing north, one could watch its slow, circular path around the pole, marking out about half of a complete circuit each evening, beginning in a slightly different place as the year moved on. While it is difficult to say, perhaps it is this distant cultural memory of motion in a circle that inspired the design of the face of a clock in some way. Before we move forward, I would also like to take a moment to try to get you to recognize just what a visceral thing the night would have been back then. In our modern culture, we have developed the ability to carry light with us in surprisingly large amounts, easy to create and manipulate. 5,000 years ago, 3,000 years ago, 500 years ago, this would have been very, very different. Outside of small fires and dwellings, the only light that would have been available would have been that of the stars, and when it was up, the moon. On a cloudy night, the blackness would have been nearly overwhelming, as our most dominant sense, that of sight, would have been completely denied to us. For those who have been caving and have descended into the earth, you may have turned out your lights and experienced that suffocating darkness. Now, imagine that sensation when standing above ground, and you can understand why there are so many tales of misfortune and terror associated with night. Of course, as civilizations were established, it became important to track not only the passage of days for various purposes, but also the passage of time during an individual day. Perhaps it was thought that a particular religious ceremony associated with the solar deity needed to be performed when the sun was highest in the sky, or that the watches of the guards on the palisades or walls of a city needed to be marked out. As human interaction became more complex, there was a need to more carefully regulate times of meeting and other social norms. Whatever the case, the tool used to divide the day would have first involved the shadow of something. While perhaps not the very first piece of technology used for this task, the easiest thing to talk about to explain the use of shadows in timekeeping is something known in Greek as a gnomon. In the simplest form, this is a vertically oriented stick placed in or on the ground so that it casts a shadow. This shadow, of course, will always be opposite the sun in the sky, and so if the sun is low in the east near dawn, the shadow will be long and point west. When the sun is high in south, the shadow will be short and point north. For those living in the northern hemisphere, it can be observed that the shadow will begin by pointing west, swing through the north, and then, as the sun sets, points to the east. In this way, with a bit of cleverness, one can determine north without a compass. The point at which the shadow is shortest will be true north on the horizon. This idea will become a key part of two timekeeping devices. The first is a tool used by the ancient Egyptians, where there is a board. Perhaps you can think of a 1-inch thick by 12-inch wide plank of wood that is maybe 2 feet long, where a short gnomon was attached to one end. The top of the gnomon would have had a horizontal crossbar nailed or tied to it, and a vertical plumb bob would be hung from the end of that to allow for the establishment of an accurate level. At sunrise, the board would be placed with the gnomon facing east, so that the shadow of the crossbar would extend along the board to the west. As the sun rose, of course, this shadow would shorten until midday, what we now call noon, when the shadow would be the shortest. Along the length of the board, a series of lines or grooves were inscribed at intervals. Each division of the board would mark out a unit of time that would pass as the end of the shadow traveled along the board from one line to the next. At noon, the board could be reversed for use in the time afternoon. Some later examples of this sort of technology place the gnomon and crossbar halfway down the board with lines on both sides. From what I've been able to find in my research, there were 2 different ways the lines were drawn. Some of these instruments had the lines evenly spaced along the board, while later versions have lines closer together near the gnomon and farther apart towards the far end of the board. So why does this matter? In the earliest versions, we find that there are 6 divisions made by those 5 lines, thus breaking the period between sunrise and noon into 6 chunks. Of course, when the board was reversed for the second half of the day, there would be 6 more divisions of that time for a total of 12. The reason the day is divided into 12 parts has to do with there being 5 fingers on one hand, plus 1 for the gnomon, which gave 6. With the flipping over for the second half of the day, that gave 12. Double that for the night, and you have 12 divisions. Those things we call hours. The interesting thing we see here is that even with the division of the day into smaller parts, there isn't an attempt to make those hours a standard length, either from day to day, or even, at least at first, during the day itself. As we said during our episode on sun cycles, the amount of daylight during each interval from noon one day to noon on the next day varies according to the season due to the sun's perceived path on the ecliptic. If you live at about 45 degrees latitude in the northern hemisphere, the sun will be above the horizon for about 2/3 of a day in the summer, but only about 1/3 of a day in the winter. Since the gnomon-based system is dependent on the shadow cast from the light of the sun, the divisions will represent about twice as much absolute time in the summer as they do in the winter. In other words, in ancient times, an hour was longer in the summer than it was in the winter. And this is always the case on a gnomon-based shadow system unless you take some very specific efforts to correct for that. The second issue is that if the divisions are the same distance apart, the hours in the morning and evening will be shorter than they will be around noon. This is why in later versions of the measurement tool, the divisions are placed further apart, though this adjustment of division gaps can only be achieved through trial and error or with the use of some other device that could track an interval of time. A better way to solve this particular problem is to get rid of your crossbar and make your gnomon a triangular-shaped vertical piece that you orient along a north-south axis. This will cast a shadow along an arc, which can then be marked off in 12 even divisions. Known as a sundial or a sun clock, this arrangement takes up more space and is somewhat less portable, but uses the sun's constant angular motion through the sky to mark out even hours. It should be noted, though, that the hours, while even through a single day, still change their duration through the seasons. The Roman writer and engineer Vitruvius, writing in around 30 BCE, included a chapter on sundials in his work De Architecturis. In this, he describes several types of sundials. The most straightforward of these is known as the spherical sundial. The best way to imagine this is to think of a cubical block of stone, perhaps a foot on each side, with a big hemispherical scoop taken out of the middle, much like one might do with a new carton of ice cream using an ice cream scoop. From the north side of the block, a gnomon is connected horizontally, i.e. level with the surface of the block, so that it projects out into the space defined by the carved out hemisphere. The shadow of the gnomon will move around the surface of the hemisphere evenly so that if the surface is marked with 12 evenly spaced lines, hourly time can be kept. As it can be difficult to manufacture such a block of stone, there are several variations on this idea. While a complete history of sundials is beyond the scope of this episode, it should be noted that as is often the case historically, the design and manufacture of these instruments usually left the realm of the purely functional and became works of art, breathtaking in their ingenuity of defining space and expressing aesthetic beauty. The first person to suggest that astronomical instruments based on shadows could be used to define an equal length hour, in other words, an hour that was the same length at any time of the year, was the Islamic astronomer Muhammad al-Battani, who used advancements he had made in trigonometry in the early 10th century CE to describe how the angles made by a shadow would change. This was first physically realized by Ibn al-Shatir in 1371 CE with the creation of a sundial, whose gnomon was aligned with the Earth's rotational axis. This approach would be first adopted in Europe in the period immediately after the Great Mortality. Now there is, of course, an inherent drawback to all sundials. They require that the sun be visible to work. As such, they aren't particularly helpful at night or when it is cloudy. In order to overcome this, many cultures developed water clocks, or, using their Greek name, clepsydra for water thief. The basic way a water clock works is that water is allowed to flow at a predetermined rate either out of or into a reservoir, and the level of the water in the reservoir is measured in order to determine how much time has passed. This, of course, would have to be calibrated in some sense to the motion of the sun. The earliest versions of the water clock were really more like timers than clocks per se. They consisted of a vessel, usually a bowl, that had a small hole in the bottom. The vessel would be placed in a larger container of water, and the water would enter through the hole. As the vessel slowly filled with water, it would sink lower and lower with the level of water getting higher. When it filled completely, it would sink, be retrieved, emptied, and then set back on the surface of the water again. In this way, that water clock acted something like a timer. The earliest versions of these sorts of instruments we have, either records of or actual artifacts of, date to around 4000 BCE in China and 2800 BCE in India. In the latter case, we have record of the sinking bowl being able to measure a unit of time equal to roughly 24 modern minutes, a standard unit of time found throughout the history of Indian culture. In later versions of these types of clocks, the inside of the bowl would be marked along the sides to note shorter amounts of time that had passed. It should be also said that so effective and practical is this sort of timer that it was used in rural areas in the Middle East and Central Asia well into the 20th century for the timing of irrigation until finally displaced by inexpensive and durable mechanical and electrical clocks. The earliest outflow water clocks that would measure the passage of time for longer than an hour we know of date to the Egyptian pharaoh Amenhotep I in the 16th century BCE. We also have passages from the Mu'la-Pen and Enuma Anu Enlil from Mesopotamia that related to filling outflow reservoirs for dripping clocks from roughly that same time. In the Egyptian clocks, 12 pillars would have been placed in the reservoir, each with differently marked spacings to account for different lengths of an hour during different times of the year. As we discussed in our episode on ancient Mesopotamian astronomy, the star tables of the Mu'la-Pen included a section that calculated the amount of water to put into a reservoir so as to account for this changing duration of an hour. This calculation, of course, was done using the typical sexagesimal or base 60 number system of the Mesopotamians, and thus the hour was divided into 60 smaller or more minute intervals, the source of our minute. One of the biggest early drawbacks of the water clock, or any system based on the pressure-driven flow of a substance, has to do with the fact that as there is less material in the reservoir, the rate of flow decreases. This means that a simple water clock will measure the passage of time too rapidly at first when the reservoir is full and there's a lot of water pressure at the opening near the bottom of the container holding the water. And then it will run too slowly as the container gets close to being empty. Anyone who has watched an hourglass will be familiar with this effect. It was the Greeks and Romans who first developed various ways to counteract this with their water clock designs by using multiple reservoirs with irregular shapes to counteract the effects of uneven flow. Additionally, these instruments often use various mechanical apparatuses to display the level of water via pointers to gauges and the like. Some versions could also be made to ring bells or gongs to mark the passage of time. Perhaps the most famous of these great water clocks was the Tower of the Winds, constructed by Andronicus of Cyrrhus in Athens at around 500 BCE. The building combined several vertically oriented sundials with a central water clock so as to function as the main timekeeping device of the city. Still standing today, the city of Athens has recently undertaken an effort to refurbish the structure, something made possible due to Vitruvius's in-depth understanding and description of the inner workings of both the structure and its devices. By the time of the rise of the medieval Islamic caliphates, pressure regulation mechanisms had been developed to solve the even flow problem, usually through the use of a float. The most complex of these clepsydra functioned not only as timepieces, but as analog computers known to be able to display the positions of the 7 planets as well as the movement of the zodiacal constellations. The most impressive of these may have belonged to the courts of the Chinese emperors of the 11th and 12th centuries. The Tower of Susong is said to have included the earliest chain drive mechanism known and had the ability to sound chimes and gongs on the hour and quarter hour, along with displaying various astronomical movements. The entire assembly was driven by a water wheel and was likely the most complex mechanical device in the world until the 15th century and the rise of European timekeeping during the Renaissance. While water clocks were, by this time, as accurate if not more so as sundials, and thus, due to their ability to run 24 hours a day, preferred, they did suffer from a couple of significant drawbacks. The first was the rate at which they consumed water. The Chinese clepsydra we mentioned a moment ago is said to have used upwards of 1,000 gallons of water every 9 hours. This required either a constant source of flowing water from a river or stream into the clock, or a nearly continuous replenishment of the reservoir by manual labor. In Europe and England, even for more modest timepieces, the reservoir was often so large that it was considered the prime source of water for municipal firefighting brigades looking to extinguish fires that would erupt in city centers from time to time. And this gives us insight into the second and more problematic issue with such devices. They weren't cheap or portable. While a large city could afford to construct an accurate and continuously running water clock, such devices were usually beyond the means of smaller towns and villages. Additionally, they were absolutely impractical for travel, leaving caravan guides and ship captains and navigators to rely on portable sundials and the positions of the constellations to keep some sense of time. As is often the case, the driving impetus for a better solution may have originated from within the religious needs of the cultures. The biggest issue was the desire to keep the hours of prayer standard and uniform for all worshippers of a faith. While Islam had the resources to train people to keep fairly accurate time using astronomical means, the Christians in the late medieval and early Renaissance Europe lacked this, especially after the Black Death carried off between 30 and 50% of the population. One solution for this would be to place reliable clocks in the various churches and abbeys across the areas overseen by the church to standardize the practice of worship and prayer. For a time, this was done with the use of candle clocks that employed meticulously prepared candles and holders that burned at a very uniform rate and thus could mark off the passage of hours with enough accuracy for the purpose. This was still, however, an expensive way of doing things, and required a certain level of labor and materials to produce enough candles to meet the demand. Another solution was the use of the hourglass. This was especially popular amongst ship navigators, as the hourglass tended to function better than any other device on the constantly moving vessel for many years after the development of more modern methods of timekeeping. As they say, necessity is the mother of invention. And so it was that the development of mechanical clocks that didn't require a water source was accelerated by labor shortages after the Great Mortality. As we move into this topic, it should be noted that this is not a break from the previous technologies, but rather more of an evolution of them away from the use of water as the source of energy to run the mechanism to other means of energy production. In other words, the technologies that have been developed to display the passage of time from the level of water in a reservoir of the water clock, or through looking at the amount of water that might have flowed through that reservoir, were adapted and modified to do the same thing with a different driver. It is here that it's useful to take a momentary digression. The development of technology most often proceeds in this way. While there are historical examples of some form of technology being invented from whole cloth, the much more common narrative of progress involves technology being adapted to new uses based on old standards. An also cited example of this has to do with the spacing or separation of the two rails of a set of railroad tracks. According to the story, this width can be traced all the way back to the standard width of Roman chariot axles and wheels, and the development of the first carts and wagons based on this axle width, along with the wearing of ruts in the trade roads that developed due to use. Now, to be honest, I'm not sure just how true it is that when the first steam engines were attached to carts and placed on metal tracks to reduce friction, that the gauge, as it is known, was based on this width. However, the story illustrates that each step along the way involves an adoption and evolution of previous technologies, often put together in innovative ways. Even so, what is really amazing when one studies the history of technology is how such small changes can have profound impacts on evolution of culture and society. For those interested in such things, let me again recommend checking out James Burke's excellent Connection series, where this type of innovation is often the subject of an episode. There are 3 of them, first done for the BBC and PBS in the 1970s, while seasons 2 and 3 were made for cable television in the 1990s. I think you can find many of the episodes on YouTube, and I really encourage you to take a look at them. They're fantastic. Alright, so back to our story. The earliest pure mechanical clock we know of is what's called the Antikythera mechanism. This was discovered by sponge divers searching an ancient shipwreck dated to around 87 BCE. Now, the function of the pieces brought up from the ocean floor remained a mystery until modern imaging techniques allowed researchers to look inside the fragments without having to take them apart, something made impossible by centuries of corrosion. This investigation has shown that the mechanism was a mechanical model that allowed the user to simulate the motions of the sun and moon. It was based on the metonic cycle and was able to predict lunar and solar eclipses. As such, while the mechanism is more of what is called an orrery or mechanical computer than a clock, its ability to simulate the interaction between lunar months and solar years merits a mention in our discussion of time. What we would more properly think of as mechanical clocks were made in Europe in the 14th century and can be found in many locations, perhaps with the oldest being in Salisbury, England. These were driven by falling weights rather than water, and often served as cathedral clocks. As was the case with the most elaborate water clocks, they often incorporated mechanical models of the universe. These models were invariably geocentric in nature and were based on astrolabes brought into Europe from Islamic Spain. The most famous of these is the Prague astronomical clock, which was first installed in 1410 and still runs today, though it has gone through many repairs, refurbishments, and reconstructions to do so. In the early 16th century, the first timepieces using a wound spring began to appear. These devices were not very good at keeping time since, as the spring wound out, it would produce less force on the mechanisms and thus run slow, as it's known. Usually kept or worn as ornamental decoration, these devices can be seen as early precursors to the watch, especially once the wind-down problem was addressed by using a varying gear ratio inside the timepiece to compensate for the diminishing force provided by the unwinding spring. The bigger development, at least at this time, was that of the pendulum clock. Galileo Galilei was the first person to develop such a device, after watching a swinging pendulum during a long church service. His design contains within it almost all of the pieces found in a modern grandfather clock. Working independently of Galileo was Christian Huygens, who developed similar clocks that combined falling weights and a pendulum to produce timepieces of extraordinary accuracy and precision for the time. The publication of this work in the Orologium in 1673 was considered a groundbreaking piece of research at the time and established him as one of Europe's greatest scientific minds. It was also at this time that clocks were first able to reliably track time well enough that a second division of the hour became commonplace. The first, of course, was the division out of the hour into 60 minutes by the Mesopotamians. This second division, then, was called, rather sensibly, seconds. The pendulum-regulated, falling weight clocks gave rise to the familiar tick-tock as the pendulum would engage and then release the mechanisms that would allow the weight to move downward ever so slightly to provide the energy to drive the clock. At roughly the same time, polymath Robert Hooke was able to show that while the pendulum clocks were the state of art in stationary timekeeping, especially when it came to accuracy and precision, they did suffer from some defects. The first was that the strength of gravity, a concept we'll discuss in greater detail in a later episode, varied from place to place on the globe. He was able to show that the rate of the pendulum's swing depended on this, and so moving a pendulum would change how it kept time. More importantly, however, he showed that a pendulum could not be counted on to keep time accurately in an environment that moved irregularly, such as on the deck of a ship. To counter this, Hooke continued the development of spring-based timekeepers by using a pair of spiral springs. His device, presented to the Royal Society in 1668, represents one of the first ever pocket watches. Just as importantly, what we can now see is that while timekeeping is still tied to cyclical behavior, the cycles being tracked have changed from the cycles of objects in the heavens to the oscillations of mechanical systems. This transition will dominate timekeeping for the next 300 or so years until replaced by electrical oscillators. While pendulum clocks would become an iconic status symbol of wealth and stability, the development of spring-powered chronometers would be the future of timekeeping. The reason for this had to do with a problem a number of you may have heard of, something called the longitude problem. While determining one's latitude, i.e. the distance a person is north or south of the equator on the globe of the Earth, is a fairly straightforward procedure involving the determination of the height of one or more stars, most notably Polaris in the northern hemisphere, finding out how far east or west one is can be a much more difficult proposition. Actually, I should say it's a much more difficult thing to do in practice than in theory. In theory, it should be just about as easy as determining latitude. Since the Earth turns 361 degrees every 24 hours, and by the way, as sort of a teaser question, can you figure out where the extra 1 degree came from? It stands to reason, then, that the Earth turns 1 degree each 3 minutes and 56 seconds. As a side note here, we can now talk about the Earth turning instead of the celestial sphere or something like that, because of the work of men from Nicholas Copernicus to Isaac Newton, who've by this time shown that it is the Earth that moves rather than the Sun by this point in history. This is a story we'll cover here pretty soon in the podcast. What the rotation of the Earth means is that as one travels west by 1 degree of longitude, the Sun comes up 3 minutes and 56 seconds later, or, in order to avoid the problem of having irregularities on the horizon, the Sun will be due south at noon that same time later. So the idea is that if you can keep track of the time at some known location, say the Royal Observatory in Greenwich, England, you can determine your longitude. All you have to do is determine noon at your location and then read a clock set to Greenwich time. If the clock were to read 12:11:48, or 3 times 3 minutes and 56 seconds, you'd know that you were 3 degrees of longitude to the west of Greenwich. This was hard enough to do on land with a pendulum clock, but it's nearly impossible to do at sea, as pendulum clocks didn't keep very accurate time on the deck of a ship for a whole host of reasons. Other timekeepers, such as hourglass, just weren't accurate enough, a reality made horrifyingly clear in 1707 when a fleet of 4 ships and over 2,000 sailors was lost off the coast of England due to poor navigational accuracy near the Scilly Islands. As a result of this loss of life and cargo, the British government offered a large cash prize to whoever could solve the longitude problem. I won't spend time here on the details of the race to collect the prize, as Dava Sobel's book Longitude does a wonderful job of chronicling the story. For those who'd like to hear a synopsis via this medium of podcasting, the Curious Minds podcast recently did a nice episode on the topic that's worth taking a listen to. The problem was eventually solved by a clockmaker by the name of John Harrison, who perfected a number of the technologies developed earlier to produce a series of chronometers that were successively smaller and more accurate, finally winning the full award in 1773 after a long and protracted battle. Harrison's timepieces, which, after some restoration, have been preserved for posterity, are truly works of art. We'll include images of them on our website, thescientificodyssey.typepad.com. The upshot of this is that it was now possible to produce timepieces that could keep time accurate to within 5 seconds over a period of months, a huge leap forward in precision. Over time, this mechanical design would continue to be miniaturized, first in watches that could be carried in a coat or vest pocket, and then something that could be worn on a person's wrist. This proved useful in many different ways, when individuals separated in space could still synchronize their actions in time, a huge advantage in military operations, for example. In the 20th century, with the development of aviation, the need to be able to quickly and accurately determine longitude for an aircraft able to travel much faster than the 10 or 15 knots of a sailing vessel made good timekeeping an absolute necessity for navigation. While one can imagine air travel over short distances or around a local airport without accurate clocks, it is impossible to think of transcontinental travel being able to take place reliably and safely enough for passenger transport in its absence. The first electrically powered clock was developed in 1814 by Sir Francis Rowlands using an early implementation of Volta's recently invented voltaic cell. This was not very good at keeping accurate time, as the current delivered by the dry cell design depended both on temperature and humidity. The first reliable electric clocks were developed by Scotsman Alexander Bain in 1840. These relied on an electromagnetic oscillator and a constant electric current, technologies that had been developed from Michael Faraday's work on electromagnetic motors. The next significant breakthrough came from the work in 1880 on piezoelectricity done by our old friend Pierre Curie and his brother Jacques. By stressing a piece of quartz crystal, they found that it produced a tiny electric current that oscillated many times a second with a very precise frequency. Walter Cady took this idea and turned it into an electrical oscillator in 1921, which was then incorporated into the first quartz oscillator timepiece in 1927 at Bell Labs in Canada. These clocks very quickly became the precision standard with an ability to keep time accurately to the thousandth of a second, and by 1932 were being used to measure variations of the Earth's rotation rate, among other things. As had been the case with mechanical clocks, quartz chronometers were continuously improved and miniaturized until, in 1969, the first wristwatch-sized models were introduced. By this time, however, the quartz oscillator had been replaced as the high-precision timekeeper in scientific applications. Back in 1879, William Thomson, more commonly known as Lord Kelvin, had proposed the idea of using atomic vibrations as the oscillator in a chronometer. While intriguing, the understanding of the nature of the atom and what mechanisms produce spectral lines would have to wait until both the discovery of the electron and quantum mechanical models to create technology that would allow for a realization of Kelvin's idea. The U.S. National Bureau of Standards created the first atomic clock in 1949, though its accuracy fell short of quartz oscillator timepieces. The proof of concept, however, did show that the technology was feasible, leading to the development of a highly accurate version based on the photon emissions from cesium-133 in the UK in 1955. So accurate was this method of keeping time that in 1967, the second would be redefined as the amount of time for a certain number of cycles to take place of the emitted photon created by the energy released when an electron flipped from one spin state to another in the atom's lowest energy level, known as the ground state. These advances in modern timekeeping, first with quartz oscillators and then with atomic clocks, have made possible a number of modern technologies necessary for spaceflight and navigation. Perhaps the most commonly used version of this has to do with global positioning satellite systems that use the ability to very accurately measure time to allow for the determination of the position of an object on the Earth within a meter or two in most commercial applications and within centimeters in military and surveying uses. Other benefits of such accurate timekeeping include the synchronization of electrical transmission of energy across power grids and cellular and satellite-based communication over vast distances both here on Earth and through interplanetary exploration. Finally, as our ability to track time has become more precise, it has allowed us to test the predictions of the two great pillars of 20th century physics, quantum mechanics, and general relativity. In a paper published this month, May of 2016, researchers at UCLA have announced the development of an optical clock that uses bursts of laser light to measure time intervals at the attosecond timescale. This means they can distinguish between two events that are on the order of 10 to the minus 18 seconds apart. Moreover, while such devices do already exist with roughly similar accuracy, this iteration is only 1 cubic centimeter in size, which would allow the unit to be mounted on computer chips, thus eliminating the need for stabilization and additional electronics to control the device. This development promises to revolutionize the scientific measurement of any number of atomic processes. Up until now, we've been discussing advances in timekeeping technology and the precision they can create, something that's reached about 1 second per 100 million years. This, however, really raises a new question. How do we define a unit of time? For millennia, the basic unit of time was the day. It was the time it took from the sun to be due south in the sky until the next time the sun was due south. Given the way we subdivided this unit, something based on the rate of the Earth's rotation, we said that a day was equal to 86,400 seconds. So how did we arrive at this number? Well, based on that ancient Egyptian shadow clock, there were 6 hours of daylight before noon and 6 hours after it. Then the night was divided the same way using a water clock. That's a 24-hour day. Then the Mesopotamians used their base 60 number system to figure out how to divide hours into more minute divisions to deal with the fact that the length of the hour changed with the season. This eventually gave us, when we decided during the Renaissance that all hours should be equal, 60 minutes per hour. As timepieces got more accurate, time was divided a second time into smaller units, again 60, this time per minute. So that gives us 60 seconds in a minute, 60 minutes in an hour, 24 hours a day. 60 times 60 times 24 gives us 86,400 seconds in a day. This seems more or less straightforward, except that there's a bit of something that's really a big step that I've sort of glossed over. When the hour length is standardized, there's a philosophical shift away from keeping time based on the motion of the sun in the sky and towards something absolute. When this happens, it's no longer true that each day has 12 hours of light and 12 of dark. Counting the hours still starts at noon, or more commonly, anti-noon, when the sun is directly opposite due south in the sky, the time we call midnight. But with each division of the interval between successive solar events being the same, days now have more hours of light than hours of night during the summer, and vice versa during the winter. However, because of the orbital dynamics of the Earth's pass around the sun, it turns out that the amount of time it takes for the sun to get back to being due south, or opposite due south, changes. So, how do we define a day? Especially after 1969, when the second is not defined as 1/86,400th of a day, but as a number of cycles of a cesium-133 atomic clock. Moreover, due to the effects of the interactions of the Earth's oceans and the moon through the times, the Earth's rotation is slowing down at a rate of about 3 seconds every 10 years. So which do we use? Time based on the rotation of the Earth, or time based on atomic oscillations? This takes us even further down the philosophical rabbit hole, and that goes to the question of what is time really? One view could be said that it is a way to measure the interval between successive events in a cyclical process, i.e., the interval for the Earth to rotate 361 or so degrees so that the Sun will be in the same position in the sky. Those who hold to this point of view suggest that all definitions of time units are just a way of relating various cycles to each other, and thus can be defined in any arbitrary way. This was the view of men such as Gottfried Leibniz and Immanuel Kant, who thought that time, along with other things like space and number, were constructs of the human mind. The other view is that time, along with space, is something that is built into the fundamental structure of the universe. This was the view espoused by Isaac Newton and perhaps Galileo before him, and so it has become the dominant scientific paradigm, especially within physics. It would be Einstein who would develop a full physical model of this philosophical position with the publications of his special and general theories of relativity, where time is conceptualized as a fourth dimension of something we call space-time, and its measurement depended on the motion of reference frames of various observers. If one accepts the first way of defining time, it seems that defining a day on the motions of the sun is the way to go. However, it is very clear that the scientific community has adopted as its working model the second idea of time as part of the structure of the universe that all events are measured according to. As such, the day, that thing defined by the interval between solar position events, is now kept by taking averages, as is the case with what is known as the mean solar day, or by adding leap seconds to certain days in specific years to keep the two definitions synced up. One final philosophical consideration, if one adopts the framework position on time, is that it seems that we can only move through time in one direction. While the reasons for this are an area of investigation in theoretical physics, the explanation seems to be tied up in something known as entropy and the second law of thermodynamics. While we don't have time to go into detail on what entropy actually is in a physical system, and no, the idea of it representing chaos or disorder is not sufficiently detailed enough to truly get at the complete idea, the second law of thermodynamics says that entropy must increase for the universe as a whole when any physical process takes place. This seems to suggest that processes can only move in one direction time-wise, thousands of movies, TV shows, and novels notwithstanding. We will delve into the ideas of Einstein's relativity theories down the road a ways, so I'd like to leave that until then. Discussing these ideas will take at least one episode, and I don't want to do the ideas an injustice by trying to shoehorn them in here. So this brings us to an end of this week's episode. As always, thanks for listening. Be sure to check out the music of the Blue Dot Sessions over at their website, sessions.blue. It's really great stuff. Also, if you can, would you mind leaving us a favorable review on whatever site you use to listen to the show? It helps us get the word out and recruit new crew members to the Odyssey. Next week, I think I'd like to spend just one more week on this digression into time. We spent a couple of hours discussing how we count it, but we've really only scratched the surface of some of the philosophical considerations related to it. So if it's okay with the crew, before we head back out into more open waters to begin our consideration of Renaissance physics and astronomy, I'd like to do just a bit more explanation of this fascinating island of time. So until then, full sails on your journey.